Welcome to the Databricks Skill Builder series. We're glad you're here.
I'm Craig Lukasik, a specialist solution architect within the CME organization at Databricks. Today we're going to delve into state schema in structured streaming applications. Many of you might already be well versed with the nuances of Delta Lake table schema evolution. However, in this session we will pivot our focus towards PySpark and explore the realm of arbitrary stateful operations in structured streaming and how that state is managed in stateful operations. The primary audience for this presentation is PySpark data engineers. We'll start by reviewing the applyInPandasWithState function, focusing on state and schemas in the context of the operation. We'll also explore various business scenarios where there's a necessity to modify the state key or value schema. Finally, we'll walk through a detailed example that demonstrates the process of evolving the state schema, providing practical insights into its application in real-world scenarios. The concept of arbitrary stateful processing in Apache Spark is a game changer in stream processing. It allows for sophisticated, customizable operations that maintain a consistent state over time. This feature shines when merging information from various records in your data stream. applyInPandasWithState is a pivotal method brought forth in Databricks Runtime 11.3 LTS, tailored for PySpark. This function mirrors the capabilities of flat map groups with state in the Java and Scala API. The operation allows a stream to execute intricate operations while preserving a state across a time. This is invaluable when integrating data from multiple records within your data stream. In the realm of structured streaming, stateful operations refer to processes that amalgate or track data across numerous rows in a stream. These operations can include tasks like data aggregations or duplicate record removal. Here, state denotes the persistently maintained information throughout the processes for subsequent microbatches or runs of the stream. A critical aspect to consider in stateful processing is the management of state size and addressing late data. In Spark, this is typically regulated through watermarks. Watermarks serve as guidelines for handling late arriving data and determine when it's time to discard old data. It's crucial to acknowledge that while these stateful operations offer substantial flexibility, they also demand a hands-on approach to state management. This responsibility includes crafting your own logic for expunging outdated state data, ensuring that it remains manageable and effective. In our discussion of stateful processing in PySpark, it's essential to recognize four distinct schemas that play a pivotal role. First, input data schema. This is the structure of the data as it enters the streaming process, the source data frame. Second, key schema of the state. This schema defines the key component of the state. It acts as the identifier or reference point for state data. Third, value schema of the state. Complementing the key schema, the value schema outlines the value part of the state, encapsulating the data we want to maintain or track, for instance, aggregate values. And lastly, the output data frame schema. This represents the format of the data after it has undergone stateful processing. This is the schema of the records that are emitted from the stream. Understanding these schemas is fundamental for effectively implementing and managing stateful operations in Apache Spark. So let's delve into why evolving the state schema is sometimes necessary in Spark streaming applications. For a clearer understanding, let's consider a hypothetical scenario. So picture this, it's 2023 and you deploy a new streaming application. The business identifies account as the primary focus for analytics. For example, within a viewing session tied to an account, you might want to track and report metrics such as the frequency of pressing the play button or the number of channel changes. In this setup, your state structure, specifically your state schemas, could utilize an account ID as the key, and the value schema of the state might encapsulate distinct values relevant to some metrics of interest. Fast forward to 2024, the business shifts its analytical focus from the account to the individual profile level. This change is driven by the realization that a single account may be shared by multiple family members, each with their own profile. Additionally, there's a need to track new metrics, like the count of ads displayed in a session. This change exemplifies a scenario where the state schema must adapt and evolve to meet new business requirements and analytical goals. Through this example, we see the dynamic nature of business needs and how they necessitate the evolution of state schemas in streaming applications. So, having established that business requirements can drive changes in state schemas, let's explore strategies to manage these transitions. A straightforward approach might be to set up a new pipeline and direct analysts to just use that updated target table. However, real world often necessitates careful planning and engineering. So let's consider some of these scenarios where a simplistic solution might not suffice. So if you have to avoid a full refresh, there might be situations where a complete refresh of the data pipeline is impractical or undesirable. Preventing duplicate outputs. In cases where maintaining the uniqueness of output data is critical, avoiding duplicates becomes a priority. Adapting to state key schema changes. Changes to the key schema of the state require thoughtful adjustments to ensure consistent tracking and analysis. This one's really tough. And lastly, handling state value schema changes, which is what we'll focus on in our demo in a bit. This has to do with modifying the value schema of the state. And this poses its own set of challenges, particularly in preserving data integrity and relevance. These various requirements highlight the need for a more nuanced approach to adapting your data pipelines and state management strategies in Spark streaming applications. So we're going to focus on a specific hypothetical case to demonstrate how we might manage state schema changes, specifically the value schema changes under some other stringent conditions. So our scenario has 3 non-negotiable requirements. So 0 tolerance for data loss. Every piece of data is critical and losing data is not an option. Secondly, avoiding data duplication. Let's assume it's crucial to ensure that the data remains unique and no duplicates are created. And lastly, no full refresh. Refreshing the entire data set is not a viable option. So given these constraints, we'll look at one strategic approach, which will be further explained in the upcoming demo. And the strategy encompasses, first, a time-bound key requirement. So we must know some sort of time boundary for a key. So for example, a viewing session, let's assume for our hypothetical situation and demo that it won't exceed 4 hours. So some sort of time-bound requirement for this strategy is needed. Secondly, checkpoint removal. So since we're going to change the value schema of the state, we're going to have to remove the checkpoint because that's where the state is stored. This step is necessary for preparing the stream for a restart with the new schema. In our demo, we will remove this persisted state data. Thirdly, the stream restart with historical context. We'll be restarting the stream at an earlier version or timestamp which predates the known time bound. So when streaming from Delta, you can use starting version or starting timestamp, and other streaming sources like Kafka offer options like starting offset. And lastly, merging into the destination. So this involves merging the output into the final destination. And in the strategy that we'll show in this demo, we'll have logic that will transition from merge into the destination into an append mode. So after a certain safe period, the strategy will switch from merge to append. So these steps illustrate a methodical approach to adapting stream processing to new requirements while ensuring data integrity and meeting those specified constraints. All right, so let's just start to talk about the demo and set the stage for the example data or sample data. So let's assume this stream will not emit records until 4 hours have passed with no new records for a key. So essentially, the logic for the demo will assume that a viewing session for a given key is done when 4 hours has passed for that key. And we're going to use the event timestamp, and we'll get into that a little bit more later. So as events arrive in the stream, the applyInPandasWithState function will aggregate a certain subset of the columns from the source data frame. These columns are named state value, like it has that word in the column just so it's clear to understand what columns are being aggregated. The stream will emit a single record for a given key. So for a given ID, it will emit a number of records. Some will be these aggregated columns that'll have the name state value in the column name. And for some columns, we'll just retain the original values. Those column names in this demo will just have the phrase other underscore column in it. And lastly, the stream will emit an additional column called earliest timestamp. So what will happen is the sample simulated data will simulate events for a variety of keys. So think of those like the account ID. And after 4 hours of events streaming in for that key, one record will be emitted. Some of those columns will have aggregate of the of what has arrived. Some of the columns for that single record for that key will just have the earliest content that arrived, and there will be an additional column added called earliest timestamp. So for our demo, we'll be using two main notebooks. And let's start with discussing the Populate Bronze notebook. This notebook is designed to simulate the ingestion of data over a series of days, beginning from a specified bronze start date. So there are some variables you can adjust in the demo code. This start date is defined in the _common notebook, which is executed within the Populate Bronze notebook itself. So you can see that %run. So a critical aspect to understand in stateful processing is the distinction and significance of the event timestamp versus a wall clock timestamp. In our demo, we will primarily focus on the event timestamp and its associated timeout for state eviction. It's important to note that state can also be evicted from the state store based on a wall clock timeout and a predefined timeout duration. So remember, the state store accumulates state for each key. It's crucial to implement an appropriate timeout mechanism, either based on event timestamp or wall clock time, to prevent unchecked growth of the state store. Neglecting this can lead to an escalating resource consumption and potential performance issues in your workload. Our example will guide you through managing these aspects effectively to maintain an efficient and stable stateful processing environment. In order to effectively demonstrate schema evolution in our demo, you will need to execute the latter portion of the Populate Bronze notebook a second time after an initial run of the cells. This step is crucial for simulating the changes in schema over time. Again, it's important to time this correctly if you're going to run this demo. You should run this section only after allowing the bronze to silver notebook to process some of the data that has already been generated. You want to be able to see some output in the target table, which is just named silver. This sequential approach helps in mimicking a real-world scenario where your streaming application initially operates with one schema and then needs to adapt to a modified schema as the business requirements evolve. By first processing existing data with the initial schema and then introducing changes, you'll get a practical understanding of how schema evolution impacts the streaming process and how to manage it effectively in a dynamic environment with this strategy. So let's summarize these 4 key steps that constitute our demo, ensuring a clear understanding of the process. So first, begin by running the Populate Bronze notebook. This setup simulates the initial data flow into our streaming application, setting the stage for our subsequent operations. Second, once the Populate Bronze notebook has done its part, switch to running the Bronze to Silver notebook. Run the Silver to Bronze notebook until you're sure some data is arriving in the Silver table. You can stop the Bronze to Silver stream when there is some outstanding Bronze data to be processed. This will help ensure that the state store has some state that has not expired. Third, run the Populate Bronze bottom section again. After halting the Bronze to Silver notebook, proceed to run the bottom section of the Populate Bronze notebook. This action is where schema evolution is simulated, introducing new data with an evolved schema. And fourth, run the Bronze to Silver notebook. Finally, we'll be restarting the Bronze to Silver notebook, but before doing so, we're going to make sure to set some necessary variables in the widgets as per the new schema requirements. This step will demonstrate how the streaming application adapts to and processes data from the schema evolution, following the schema evolution. So these steps collectively offer a comprehensive demo of managing schema evolution in a streaming context, reflecting practical challenges and solutions in a stateful processing environment. So here are the variables used in the consuming notebook Bronze to Silver. So debug mode. So throughout the demo, there are numerous debug messages that are printed to provide a transparent view of what's occurring inside the for each batch and applyInPandasWithState functions. This feature is invaluable for understanding the mechanics of our streaming application. Next is max files per trigger. This setting allows you to control the volume of data processed in each microbatch. Experimenting with different values, even 1, can be enlightening when looking at the logs, although such a low value is not typically recommended or practical for production environments. Now let's talk about the safety, run duration, and checkpoint iteration variables. These are integral to our scenario under the assumption that a viewing session does not exceed 4 hours. When business requirements necessitate a state schema evolution and the Bronze to Silver stream is stopped, the exact contents of the state store might not be readily discernible. To avoid reprocessing all the data, we want to use these variables to strategically reprocess only a portion of the historical data. The starting version variable dictates the delta version of the source table for reprocessing, while checkpoint iteration is adjusted post-interruption and during state schema evolution. Changing this value means that a new checkpoint directory with an empty state is created. Safety run duration determines whether data is merged or appended into the target table, based on the time frame set in relation to business needs. So in our context, we assume that it's about 4 hours or so. Appending data is safe and will not result in duplicates. But for the demo, we're going to use a much shorter duration because we don't want to wait around for 4 hours. So in summary, the approach demonstrated here addresses state schema evolution by removing checkpoints and the associated state store data, reprocessing a calculated amount of historical data, and employing merge only as long as necessary. We avoid indefinite use of merge due to its operational overhead, highlighting a strategic balance between efficiency and data integrity in stateful streaming applications. The provided code snippet is used in the applyInPandasWithState method. Here's a summary of its key functionalities. So the debug mode configuration. So when debug mode is active, the function is configured to display all rows and columns of the pandas data frames it's operating on for logging, and just so you can see what's happening with those underlying data frames. Secondly, there's key extraction and previous state retrieval. The function begins by extracting the session ID, or the key that we're using for our state, from the provided key tuple and retrieving any previously stored data from the state object. Third, there's state timeout handling. If the state has timed out, and we're looking here in the code, if the state is timed out, the function prints a timeout message for the session ID. It removes the state and prepares the previous state data frame for emission, including re-indexing it to match the output columns, and it yields it. Data frame consolidation and state update. If the state hasn't timed out, the function consolidates the data frames from the iterator of pandas data frames and any previous state into a single data frame accumulated DF. The first row of this joined data frame is converted into a tuple, which is then saved as the updated state in the state store. Right there. State timeout update. So this function right here updates the state's timeout timestamp by adding a specified number of hours. This effectively extends the timeout period for the state. And again, this is using the event timestamp. There's a different function if you're using wall clock timeout for evicting or timing out the state. And you can see here at the end, so if the state hasn't timed out, yeah, we do all this stuff, but we're yielding an empty data frame. That's because we don't want to emit data frame until we've done the aggregates for the session and that timeout has kicked in, which indicates that the key, we're done receiving events for that key. The viewing session is timed out. So basically no records are going to be emitted as events are streaming in, and then after a while the timeout will happen for that key and it'll emit the aggregated data and the rest of the structure that we mentioned before. So this code is a complex example of a stateful streaming processing in Spark, demonstrating the handling of timeouts, state updates, and conditional debugging for intricate data processing workflows. The provided code snippet here is designed for use in the forEachBatch function. It showcases a strategy for handling batches of data in a streaming context that we mentioned earlier, where it's going to decide if it's going to merge or append. And here's a summary of the functionality. So timeout calculation for safety period. So the code initializes with the current timestamp, and then it calculates an end timestamp by adding a safety run duration in hours. So the safe period pass function checks whether that current time has surpassed the end time. The function returns true if the safety period is passed. The forEachBatch function down here is what we'll look at next. So this takes in a data frame as an input. And whoop, hold on, sorry, I fast forwarded a little bit. So if the checkpoint iteration is less than 1, which means this is the first time the stream is running, so we can assume that we don't need to merge, or if the safety period is passed, it will use append into the target table. If the safety period has not passed and the checkpoint iteration is 1 or more, the function uses the SQL merge operation. We got the cluster up, and we've got clean logs. I am going to actually start off by cleaning up my previous run. So I'm going to just set this variable here, clean up to yes, And I'm going to click Run All. So when you run this cleanup, it will drop the tables involved in the demo and remove the checkpoint directory. And the checkpoint directory is really, it has a sort of a root that is specified. And then if you remember from the previous slides, we will create a new checkpoint directory for every time we need to evolve the schema of the state store. All right, so this cleanup has run. So now I'm going to run this one time. So a lot of these variables that are printed out here, these parameters, are set in this common notebook, which is over here. And but you can override them as shown here. So this first variable that we're going to explicitly set here says there's 3 columns that we want to really track aggregates for. And there are 4 columns that we just want to retain the earliest value of. And this populate bronze, so this is going to produce fake data, and it's going to use these variables to guide how much data it generates. So I'm going to run this whole thing now. And then I'm going to jump over to one other notebook. So in the demo, there's a notebook called Explore. So I'm actually going to clear this out just so I know we're looking at fresh thing here. Actually, I don't need this. We can ignore that. So we just want to look at this bronze table. So we should be populating this bronze table now. So let's just check to make sure we're getting data. All right, so the populate bronze table, so this is a data simulator. It's creating fake session data. The session key is called ID, so think of this as the key. So going back to our example, you can think of this as the account ID or the session. Or actually, it's better to think of it as like a session ID that is unique, but will receive multiple events. So this is basically saying we've got 4 events for key 0. Looks like they're coming about an hour apart. And you'll see this event timestamp is based in 2020. And I did this just to kind of illustrate that when it comes to the stateful processing, you want to be mindful of event timestamp versus wall timestamp. And this demo uses event timestamp for the state management. But this is what the raw data looks like. And so we've got some data being generated. Now what we want to emit are aggregates. So our target table, we don't want multiple records for a key. We want 1 record for each key, and we want to add up the values for these different columns that have the word state value. And then in our target table, we're going to add another couple timestamps. But first, let's run our notebook that will populate the target table. So I'm going to clear state, and I'm going to just make sure we're fresh. And I'm just going to go back to our cluster. And right now, our logs are pretty quiet. There's not a lot of things that we see in the logs here. And that's going to change as we run this, as we run the bronze to silver. So far we've populated the bronze table, but now we want to process that in structured streaming. And I'll scroll up and I'm going to very quickly walk through some of the rest of this code and what's going on. So we're using that. Actually, I'm going to start this first. I'm going to set this back to 0. And to make this run fast, we'll just keep this at 100 files per trigger. If you want to really sort of see the logs and understand what's going on with the function underneath the hood, you can set that to 1, and that'll give you just a little more of a fine-grained picture of how values arrive and are processed in those functions, because there's a lot of debug messages within there. All right, so this we'll set up some common variables. We have these specific widgets that will help us with the challenge of the state schema evolution. We covered those already. There's some code to just establish the schema. So we mentioned the importance of, we have the state schema. We're just worrying about the value schema of the state. The key schema we're going to keep constant. It'll just have one column, which will be that ID. Our output columns are going to include a new column called earliest timestamp. So that way for a given key, we'll know when the first event arrived and when the last event arrived. And let's see what we have here. So this is print some of that out. There's a couple functions that help with, so I'm going to scroll down here. So this function here is the function used within the applyInPandasWithState. It operates on an iterator of data frames. So there are a couple functions that help make that easy in terms of operating within just pandas data frames. So first of all, when state is retrieved, so initially there's going to be no state, but when state is retrieved, I'm going to jump up to that function, df from state. When state is restored from the state store, it's a tuple. So we take that tuple and we are reconstituting a pandas data frame. So when we store the tuple, we're keeping those columns in a specific order. And when we reconstitute this pandas data frame, we're making sure our new data frame has that same column order. All right, I'm jumping back to our applyInPandasWithState function. So df from state, we just talked about that. And then this other function, consolidate dfs, helps us sort of do the aggregation of the iterator of data frames. So I won't go into those functions now, but basically there's one function that kind of consolidates the iterator, and then there's another function that just consolidates a single data frame and aggregates down the state columns. And you can see here how we get this earliest timestamp by taking the min timestamp on that consolidated set of data frames. All right, so I'm going to stop talking. I'm going to run this, and we'll see what happens. We've got debug mode on, and let's see what happens. So I've got a display here of the output data frame. So just a tip, if you're debugging or as you develop a stateful application, I think there's a couple tips that I will make, and actually I'll just share them now. So using a single node cluster is a little bit easier during development just because you get all your logs on a single node. If you're using a multi-node cluster, it can be a pain to have to go to the executors and try to sort of tie everything together to make a coherent picture. During development, use a test data set. That way you know what to expect. In our case, we know we have a simulator that generates fake data, but we know it's going to generate so many records for a given key, and we know we should be able to aggregate that and get a certain result. The third tip is just be careful with those schemas. It's sort of, I think within PySpark, it's a little bit more dangerous from the developer's perspective in that you can put stuff into that tuple that gets stored in state, but you got to be really careful to make sure the structure and the column sequence of what you're storing in state matches up with what you're pulling out of state and emitting and so on and so forth. With the Scala and Java API, you get a little bit of better sort of type protection. And then lastly, just make sure you're cleaning up state. You don't want to be accumulating state for keys. If you have a flaw in your logic that would result in a key not being evicted from state, that could just snowball into a workflow that just eventually comes to a grinding halt. So think about that when it comes to your test data set. All right, those are our development tips. Let's go back to the demo and see how we're doing here. All right, so what do we see? So this is our display. So first of all, within this display, we can see how we're doing in terms of processing the data. And this is important because in this demo, we ran the populate bronze once, but we're going to want to run it again after we evolve the schema. So let's take a look here. So this display is done, and let's just take a look at what we see. So for a given ID, so we see it's consolidating or aggregating these columns that have the state value word in it, and that's what we expect. So the test data set generates 4 events per event hour, and after that event, the latest event timestamp is 4 hours older than the newest event timestamp. That's when the data, when the applyInPandasWithState will time out the state and emit a record. So we can see that the numbers line up. So we get 4 here. These other columns in our test data set or in our scenario, again, think of these as values that might be like, device, operating system, or username, or things that aren't going to change over time. So in our case, we didn't want to see these values change. And I can't remember in the code if we take the latest or the earliest, but this is just to show that for a stateful processing stream, typically there are some columns that you're aggregating on and some columns that you don't really need to build a list of. You just need the one, to retain one value of it over time. So these are the additional timestamps that we added. So we can say that for key 20, the newest timestamp was 12, and the earliest timestamp was 10. And then this emit timestamp, we just added using the current timestamp. So that is an actual, current timestamp. Just added for the heck of it. So let's check our for each batch. So for each batch is running, and actually, let's see if this is done as well. Looks like it must be done, but I'll double check here. So we can see that, we have nothing outstanding. I'm gonna go ahead and just stop this notebook. I'm gonna detach and reattach. And we're going to take a quick jump into the log and see what we see here. So I'm going to just refresh the cluster logs and let's see what we see. All right. So what do we see here? It might be hidden further up. All right, I'm not going to worry about that right now. So what I was looking for, which just trust me that it's there, is in the for each batch, we should be seeing that it was using an append, because we haven't worried about evolving the state yet. So when it inserted into the target table, it should just be using an append. So that was one thing I wanted to see in the logs, but we're not going to worry about that for now. But in the standard error, a lot of this is coming from our debug messages. So we can see we're saying, okay, we've detected a timeout and we're going to emit this data frame. I'm going to scroll a bit up more. Yeah, so this is another part of the debug messages where we're not timing out yet, but we've got a new event that's come in for this session ID or this ID, which is our key. We have pulled some data out of the state store. So it had 3s. So we've already done some aggregation. And now after adding our new data that arrived, we get our updated aggregates. So these log messages can be kind of fun to just explore as you're developing your business logic to see exactly what's happening in these functions. And in practice and production, you wouldn't actually want to be logging too much. So just be mindful of what you log. And that's why in the example here, you can turn off that debug mode. All right, now let's go and just visit where we are here. So, all right, so we ran populate bronze. We ran the bronze to silver, and let's just double check what we see in our silver table. So I've got this exploration notebook, which is also part of this. We know what's in the bronze table, so we get all these. These are sort of our raw bronze events. We know that our data simulator is creating 4 records for each key. But in our target table, we just want 1 record per key, and so let's just check that out here. So this is telling us that, every key only has 1 record in the output table. And then we can take a look at what's in that output table. And as we expected, we know we have these 3 columns that we're tracking aggregates for. We know this is the sort of newest timestamp, and the earliest timestamp is logged over here. And our wall clock timestamp of when this was processed in real time is generated here. All right, so that just tells us we've done step 1, we've done step 2. Now the fun stuff. We're going to go back to that populate bronze notebook, and we're going to generate some more data, and we'll be adding another column that we want to capture aggregates for, and we'll be adding another column that we want to not capture aggregates for, but just capture the data. So at the end of this notebook, you can see that there's a couple of variables that get incremented. So next time we run this, we're going to have 4 columns that we want to capture aggregates for. So I'm going to start here. So just be careful. The second time you run this notebook, you want to start down here. So I'm just going to go run this, and this will start here. So I'm going to just make a note here of this delta version. And when we go to our bronze to silver, we're going to want to know that we want to go at least earlier than, I think it was 120. So we'll go back to maybe 100, delta version 100. We're back at the bronze to silver. Now the source table schema has evolved. The number of columns that we want to track aggregates for has evolved, which means our state value schema needs to evolve. And since the state schema doesn't evolve, that's where our strategy for dealing with it comes into play. And that strategy means, first of all, we want a new checkpoint location. So this parameter up here, just changing that value will give it a new location. I'll show you where that's set way down here. So that checkpoint location will have a new directory. So, so that means whatever was in flight in terms of being processed may have been lost. So we need to go back in time a little bit for our source that we're reading from. So we're reading from the bronze table, and where is the code? So this starting version, we mentioned earlier we wanted to start it back at around version 100. So I'm going to set that to 100 here. And then the safety duration is going to come into play now. And let me just scroll down to where that is used. So the safety duration is something that is kind of a, makes some assumptions on the business logic. Here we are. So the safety duration is used to figure out, you know, from the time the stream starts, has this safety duration in hours passed. So, you know, a minute or minute and a half or so, right? So in our demo, that's a pretty short safety duration. It might not actually even work for us. We'll see. In practice, the assumption is that, you know, once a stream has been running for a number of hours and there's a pretty good confidence that those sessions have ended, what will happen is we want to switch from using a merge to using an append. So basically, if that safety period has passed, we want to use an append just because it's more performant. But until then, we want to merge because we don't want to duplicate data in the output. So by going back in time, by adjusting that starting version, we try to ensure that we don't lose any data. And then by using this safety duration and merge, we try to ensure that we don't duplicate any data in the output. So let's give this a whirl. So I'm going to start this, and we're going to process 25 files per trigger, and hopefully that's enough for us to switch from the merge to the append without duplicating output. If we do duplicate output, you know, in practice, like I said, this duration for using merge should be a bit longer, but we don't want to sit around too long here because that's using a wall clock time. So let's just get this stream going. Let's take a look and just make sure we're starting where we want to start. So our source reservoir version, yep, it started kind of around where we wanted it to. And let's go look at our log files because we should see, I'm just refreshing this here. We should see that, yep, it's using merge right now because that safety duration has not passed. And I'm going to just refresh this until it does. Let's see how much longer we have. Still a little bit of time till 6. Actually, well, we might have processed that data. Oh no, there we go. All right, so it switched from using a merge to using append. And let's just take a look here and see how we're doing. So we're still cranking through the files. So we might actually end up with some duplicate output just because that safety duration might not have been long enough. So let's go take a look in our exploration notebook and just see how things look. So I'm just going to run everything here. So first, the first query is going to look at the bronze table. So we should see, you know, since we ran that populate bronze 2 times, that second time added these new columns. So for the earlier IDs, we know that they didn't have those values, so we expect them to be null. So I'm going to just change that to descending. And yep, so the newer keys have values for that. It looks like we did end up with duplicate data. So demo fail, but as I mentioned before, this is just an artifact of us switching from merge to append a little bit too soon. So it looks like about 35 keys ended up with duplicates being emitted. So we weren't safe enough, but that's kind of what we get with a demo and trying to keep it quick. I don't want to have you sitting around here too long. And then we can see in our output table, if we, let's just run this here, our newer IDs, we should see that they're getting the aggregates. Yep, and the new column is added that has the proper aggregates. So the demo, a little bit of a fail just because we see the duplicate output, but the reason we see the duplicate output is that safety duration wasn't long enough. We could fix that by just rerunning this, by stopping this, creating a new checkpoint, and giving it a longer period of using merges. That would totally work too. But for the purpose of the demo, good enough. So just to recap some of those development tips. So as you're developing one of these stateful pipelines, using a single node cluster and some strategic debug messages can really help you just keep track of what's going on with the keys and the schemas and so on and so forth. It's much easier on a single node cluster to look at logs than to try to track down log messages on the executors, because those print statements in that applyInPandasWithState otherwise are going to be found on the executor machines. Using a test data set is helpful because you can sanity check your expectations. So in this demo, we had a pretty constrained test data set generated by that Populate Bronze notebook. We want to be careful with schemas. So be mindful of the sequence of the columns on the output data frame and how you sequence columns when it comes to the state. Because if you remember, when you store the state, you're storing a tuple. But if you're doing aggregate operations, you're going to want to reconstitute a data frame perhaps from that tuple and do some data frame, pandas data frame operations, and then store an updated state. And then in the code that we showed here, we have cleanup of state. So that's important. If you're not cleaning up state for a given key, your job is going to grind to a halt and somebody will not be happy. So that is this demo and everything in a nutshell. So thank you for your time. One more thing. So there are future enhancements on the horizon for Apache Spark, Arbitrary State API v2, and we can probably expect to see some of this come to Spark in this calendar year 2024. On part of the goal is to include Schema Evolution. It's not entirely sure what that will look like, so this strategy that we outlined in the demo might still be useful, but we should see some improvements on this new with this new state API. So that's it. Thank you much and have a great day.